All right. So it is 3:30. Go ahead and get started. Yeah, how's everyone doing? Did you guys have a good spring break? Hopefully good. Um, cool. Well, I went to Lake Tahoe for the first time, so that was pretty cool. But yeah, yeah, I just want to talk a little bit about some housekeeping before we get started. So again, we will be having checking Wednesday, or excuse me, checking Tuesday today. I think that's all I wanted to say about that. So again, yeah, we'll stop at 4:30 just to give you guys a chance to take a look at your email. Also, yesterday I did send out another email about a bonus point opportunity that you can engage in if that's something that you'd like to do. So like I mentioned in the email, I was looking at the Getting to Know You survey that you guys filled out at the beginning of the semester, and yeah, about 42% of you mentioned that, participating in the Zoom chat was one way that you wanted to, yeah, try to remain engaged in the class lectures. But I realize, sometimes like I've heard this like when teaching Zoom classes in the past, where it's like, some people might want to participate in the Zoom chat, but like they feel like if they're the only one doing it, it's a bit weird. So basically to incentivize, give you guys a little bit of a bonus point incentive, I guess you will, I guess if you will, to boost class participation. Basically what I'll be doing at the end of every class is giving you guys a participation score. Now this participation score in and of itself is not a bonus point, but basically it contributes to an overall class ranking that I'll be calculating at the end of every class, which basically, like I mentioned, if you attend the lecture for more than 60 minutes, you get 1 participation point. And for every chat comment, you get 0.2 participation points. So basically you max out at 2 points in every lecture. And so at the end of the semester, whoever has the top 10 participation points in the class has the opportunity for either some bonus points or the opportunity to essentially not do as much of the project as your other classmates might. Yeah, and then also something that I mentioned is like, I do get quite a lot of people who ask me for recommendations in this class, but some people that ask me for a recommendation, I don't really know you that well. Like I don't, there's not much I can say other than like, oh, this person got an A in my class. So by, having that rank metric is like, it's something else that I can point to, if you will. So yeah, so just something to keep in mind. All right. Yeah, so that's basically all I wanted to say. So yeah, any questions on that? Okay. And then also, like I mentioned, I'd like to be posting, excuse me, the specifications for the project, the final project within the next few weeks. This is a group project. Unfortunately, I have really large class sizes. Well, my other class, which basically prevents me from allowing too many individual based projects. So do start thinking of who you might want to work with in a group. That's another benefit of coming to class. You can meet people in the Zoom breakout rooms. But yeah, I'll also be posting some information about how to find group mates if that's something that you're interested in. And you can also start thinking about the data sets that you might like to explore in your group project. So generally speaking, like I mentioned, the main specification for a data set is that it should be clusterable. So therefore, make sure that, you're able to see some sort of a clustering structure in that data set. So yeah, so if you have any questions about that, projects, anything like that, yeah, feel free to let me know. All right. Any other questions before we get started? Okay. All right, cool. So we're going to wrap up with Unit 9, which was, again, if we recall, we were talking about fuzzy C-means, which again is the fuzzy clustering extension of K-means. So last Thursday, we had started talking about our application in which we wanted to apply fuzzy C-means to the MNIST dataset to learn more about the observations in that data set. And, ideally, we'd like to be able to take, use our insights to perhaps give us some insights as to how we could better design a supervised learning algorithm. But yeah, before we get back into that application, I just wanted to talk about a few pros and cons of the fuzzy C-means before getting back into that. So we want to remember, The benefit of fuzzy C-means is that it allows for you, basically your output is a fuzzy clustering membership score. Or in other words, to some extent, all observations are assigned to all clusters. Now, it could be the case you get this very hard fuzzy clustering where, a given observation is like 99.99999% assigned to one cluster, which might be what you want to end up seeing if that particular observation is well clustered or it's very centrally, it's very far away from other clusters. On the other hand, we saw scenarios in which, we have these straddle node observations in which they straddle, 2 or 3 or however many clusters. So it doesn't quite make sense to assign that observation exclusively to just one cluster. So therefore, in scenarios such as this, when your clusters are overlapping or particularly close to each other, fuzzy C-means is a beneficial algorithm to use because it can reflect that the uncertainty that we might have about which cluster those straddle nodes should belong to. So it can basically help us reflect that uncertainty about the straddle nodes, but reflect more certainty about the observations which are not straddle nodes. Now, another benefit is that it tends to be better than K-means at identifying clusters when the clusters are overlapping. So I see a couple questions, so I'll get to that in a second. However, we want to remember that fuzzy C-means is simply just a fuzzy extension of K-means. So we're still using this concept of a mean. We're still using this concept of inertia. And so because of that, fuzzy C-means also tends to have a lot of the same drawbacks as K-means. So in other words, it tends to be not as good at identifying clusters that have different sparsities, clusters that are unbalanced in size, and data sets, or identifying clusters when the data set has noise and outliers. And then also something that you want to think about is that K-means is also more computationally efficient than fuzzy C-means. Okay, so someone's asking, will ranking start from today's lecture? What about previous lectures? So given that I wanted to basically give everybody like an equal opportunity, I didn't want the people who weren't coming to class to feel like they didn't have any hope of, getting the prize, if you will. So basically, when it comes to the bonus point opportunity, I'm starting the tallying as of today. However, I will retroactively count up your particular participation that you've engaged in, starting from the beginning of the semester. So for instance, if you were coming to me for like a recommendation or something like that, I would look at the whole semester in terms of your participation. But, to get the prize, in order to make things fair, I guess you could say, or motivating, I'm starting it as of today. So someone's asking, so I will provide some backup data sets for the project if you don't want to pick your own. So only the top 10 ranked students will get the bonus points. Yeah, so that's correct. Okay, and basically what I'm going to do is every other Friday, I'll post on Canvas your participation rank. So 1 through 60 to give you a sense as to like how close you are to the top 10, basically. So you can think of it as like a fun little game. I don't know. It's not meant to be too serious. All right, any questions on pros and cons? All right, so let's get back to the MNIST application. Okay. So we didn't get to say too much about the actual algorithm itself. We're simply just looking at the data set. And so this is our first time exploring a image data set. We're going to explore this MNIST data set actually in quite a few algorithms that we're going to be discussing in the next few units. And this is our first image data set that we've dealt with. So some of the preliminary analyses that we might want to explore are going to be a little bit different. So, one of the preliminary analyses that we had explored for this image data set, as well as, it's a good idea to use this for other image data sets, is to, for instance, take the average of each image corresponding to each of the 10 digit types to get a sense as to how much variability, there are in each of the digits here. Someone's saying that this data set has been haunting me since Math 257. Well, the nice thing is there's actually hundreds of MNIST variation data sets that exist out there. One of those, so we're going to be exploring in the homework assignments, for instance, like a fashion MNIST data set where it's like shoes and coats. So we're not going to be just looking at numbers here. There's actually a wide variety of different applications. However, like we mentioned, this is the benchmark data set for a lot of machine learning analyses. So a lot of people like to explore this data set here. So because we'd like to cluster this data set, first it's a good idea to see if there exists a clustering structure. So we've explored this, the TSNE algorithm before. So we are seeing evidence of a clustering structure. We've kind of already explored this on Thursday. But yeah, for instance, something interesting that we noted is that for the most part, there is a relatively strong association between the digits and the clusters that the TSNE algorithm identified. So this might, for instance, give us an indication that, a lot of our supervised learning algorithms are going to have an easier time identifying most of these digits here. However, for instance, something that we noted is that there actually look like there are 3 subclusters or 3 perhaps different types of 1 digits. Maybe some people write a 1 like this. Maybe some people write a 1 like this, something like this. So this can be a very useful insight if you were planning on building a supervised learning algorithm, because it can maybe give you a sense as to telling you that your algorithm might have a more challenging time identifying the ones, for instance. Now, what we're choosing to focus on here is, is using fuzzy c-means a good idea? Is this going to be a useful algorithm to use? And so based on what we're seeing here, yeah, there could be some indication that using a fuzzy clustering algorithm, such as fuzzy c-means, might be useful. Because again, we are getting a couple of clusters which are overlapping with each other. So therefore, we'd like to, use a fuzzy clustering algorithm like c-means, which can basically reflect the uncertainty of the cluster membership, particularly for these sets of observations here, for instance. So we're also going to use these TSNE plots as essentially a visual guide to help us select, what is going to be the best P parameter. In other words, the best fuzziness parameter to, which we discussed on Thursday, toggles the amount of fuzziness overall in our clustering. So given that there's overlapping clusters and we'd like for our algorithm results to reflect more nuanced cluster membership, it seems like fuzzy c-means is going to be a good idea. Okay. Now, we also want to think about, what number of clusters should we ask fuzzy c-means to give us, essentially. So much like we've seen with the other clustering algorithms, there's a variety of ways that or a variety of techniques that you can use to find the best number of clusters. So for instance, you might use the TSNE plots. So, based on your interpretation here, you might say, the TSNE plot is suggesting between like 10 to 13 clusters. Wait a second. Oh, for goodness sakes. Ugh. No, I'm mostly like OneNote most of the time. The only time that I hate it is when it's doing this stupid stuff. Yeah, so this might be an indication based on how many clusters you see in this TSNE plot. You could ask fuzzy c-means for anywhere between 10 to like 13 clusters. Also, for instance, you could use a fuzzy c-means elbow plot to give you a sense as to how many clusters fuzzy c-means is detecting. So that would be, a more straightforward method for detecting, actually, if you know that you plan on using fuzzy c-means. So a more complete analysis would have tried both of these techniques at the very least. We're simply just going to rely on the TSNE plot for now, but a more thorough analysis would have tried multiple methods. So we're going to see that in the homework assignment. So we're gonna, we're gonna go on the lower end here. So let's look for 10 clusters in fuzzy C-means. So unfortunately, the C-means function, or basically fuzzy C-means, is not a function that scikit-learn has. So we needed to install that fuzzy C-means package ahead of time. And then unfortunately, another downside is that the C-means function does not operate in the exact same way. For instance, the K-means function does in scikit-learn. So it has a different set of specifications. So if you want to just use a naive implementation of C-means, you can use this C-means function here. Now, a key distinction about that you want to consider when it comes to using fuzzy C-means is actually what should show up on the rows of your input matrix and what should show up on the columns. So generally speaking, when we've clustered all other data sets, the rows of the input matrix were meant to be the observations, and the columns of the data set were meant to be the attributes. So with the C-means function, it's actually going to be opposite. So the rows of your input matrix should be the attributes, and the columns of your input matrix should actually be the objects you want to cluster. So I'm simply just going to take my original X matrix, which had the observations or the images on the rows, and I'm simply just going to transpose it here. Okay. And so I knew that I wanted to look for 10 clusters. So I'm gonna use C equals 10 clusters here. Now I really don't yet have a sense as to what the best fuzziness parameter P might be. So the P in this function is actually represented with M. So I'll just make a note here. Okay, I'm just going to start off in a naive implementation of fuzzy C-means. So I'm simply just going to pick a very low value of P, or something that's very close to the lower bound of 1, non-inclusive. Okay. A couple of other things I need to actually specify for this function. This function is the error, or basically an error term, which indicates, if your algorithm is, or so basically, if the change in weighted inertia is less than this specific number, that's when your algorithm should stop, or that's when the fuzzy C-means algorithm should stop. You do need to specify a maximum number of iterations that the fuzzy C-means algorithm should execute before you essentially stop with the best one. You should also, specify a random seed, because this is a non-deterministic algorithm. Okay. So there's a couple of more or less useful outputs that you get in this fuzzy C-means algorithm. So we're going to explore each one of these outputs. So the first output is your centroids, your final centroids that you might want to explore. And then another output, actually I'm going to use a different color here. Another relevant output that you want to explore is this W matrix, in other words, your fuzzy clustering membership matrix. You can take a look at the notes to explore what some of these other elements are. They tend to be not as important, if you will. But then another useful metric that we're going to explore is this normalized Duns partitioning coefficient of the fuzzy clustering matrix W. We want to remember this is a 0 to 1 metric, which evaluates how fuzzy your fuzzy clustering membership matrix is. Okay. So we're going to explore some of those outputs. So for instance, so we can take a look at the centroids. Okay, so take note, the centroids centroids matrix is basically going to be 10 rows, each with 64 columns, or in other words, each of the pixel values for each of those columns. Okay. And furthermore, your W matrix is going to represent, it's actually going to be flipped. It's not necessarily in the order that we might want it in. So the technical output of or the initial output of that cluster membership matrix is, in this case, going to be, let's see here. Yeah, so you're going to have your 1,797 observations actually showing up on the columns. So you want to remember your observations are still on the columns, and then your 10 cluster membership rows are going to be, or values are going to be on the rows. So generally speaking, I like to transpose that fuzzy clustering membership matrix such that it's a little bit more readable. So basically I have, each of my images or each of my observations on the rows, and then the corresponding cluster membership score values are in the columns here. Okay. And so if I want to get a more visual sense as to like what this cluster membership score matrix is going to look like, this is what I get. So simply just by looking at this cluster membership score matrix, what I can see here is that this is a very hard assignment. Or in other words, every observation is mostly assigned to one and only one cluster. Okay. Yeah, so someone's asking, can you explain the W matrix again? You said the output is flipped. Yeah, so the initial output for W will have basically your observations or your images on the columns, and then basically what we have here will be in the rows. I like to transpose the output so it's a little bit more straightforward. So this is what I'm looking at here is actually my output that has already been transposed. It's a little more straightforward. Something else that's going to be useful is, unfortunately, I don't like the c-means function as much. It's not as, I don't know, it's not as clean as the scikit-learn functions, I guess you could say. But if you ever want to extract the weighted inertia of your final clustering, or your final fuzzy c-means clustering out of all the iterations that the algorithm went through, you can use the history output from c-means. And basically what this shows you is the weighted inertia at each iteration of the fuzzy c-means algorithm. So this gives you a sense as to how many iterations the algorithm went through. And so basically the final value here is actually the weighted inertia of the final fuzzy c-means clustering that was returned. So for instance, if you wanted to, basically create like a fuzzy c-means elbow plot, where you put that weighted inertia, on the y-axis, this is the value that you would use here. So you would want to extract the final value here. Okay. And yeah. Then we can also take a look at the normalized Dunn's partitioning coefficient of that fuzzy clustering. And we can see that that value is 0.99. It's really close to 1, which indicates this is a very hard assignment. And we can also see that by looking at the matrix as well. And this also makes sense, right? Because you want to remember that we set our fuzziness parameter P to be very low, right? So we set this to be almost at the absolute lowest bound of what P can be of 1. So basically the lower your P or M parameter is, the harder of an assignment. So we're going to explore if this is a really useful fuzzy clustering result. Like, is it, given how hard of an assignment this is, for all intents and purposes, we could have just run k-means and got the same results. So we're going to use TSNE plots to really give us a sense as to how good of a fuzzy clustering this actually is in just a second. But let's also use another technique for giving us more nuanced insight about how fuzzy this fuzzy clustering membership matrix is. So what we might decide to do is for each observation in the data set, we might decide to find the highest score value that corresponds to it. So for instance, observation 0, its largest value was a 1. So that would correspond to this. But for instance, the final observation in the data set, we can see that its largest cluster membership score was a little bit lower. We were slightly less certain about where this observation should belong. So we find this largest value here. So basically, we can take our W matrix, our fuzzy clustering membership matrix, and to find these highest row values, we can simply just transpose the matrix temporarily and find the maximum column value of this transpose matrix. Okay. So basically, this gives me the highest membership score for each observation in the data set. And then I can basically put that into a histogram to give me a little bit more nuanced insight. Okay. And so, yeah, this tells me that, for the most part, every single one of my observations has a very hard assignment. So its highest cluster membership scores we're very close to 1. On the other hand, there's a couple of observations. Even when we set this fuzziness parameter to be really low, there's still a couple of observations that we were much less certain about what cluster they should belong to. Or in other words, the highest cluster membership score for some of these observations was only something like 0.75. So we might decide to, for instance, explore, take a look at those images and see, why was their particular fuzzy, or why was their particular cluster membership scores comparatively lower? Could it be that, maybe those images are less well drawn? Are they a little bit less obvious? And so that's something that we do here. So for instance, we take these highest membership scores, this Panda series, we can sort it. And this tells us that the image with ID 8, its highest cluster membership score was something comparatively lower, 0.56. Okay. And so this is what that particular image looks like. So we can take our original matrix X. We can use the iLock function to focus on just the observation with index value 8, or the 8th, the index value 8. And yeah, so basically this image should be an 8. This is what it's meant to represent, but I don't know. Looking at this seems to be a pretty sloppy 8. So, for instance, that could be the reason why this particular observation has so much uncertainty in its cluster membership. Like, what does this even look like? Is it a 3? Is it an 8? So this can be one technique for, finding observations that, this particular data set are, it makes sense that they, don't have a very strong, cluster membership. And that can be, that can yield useful insights when it comes to building your supervised learning model as well. Okay. Any questions on that? Okay. So that was just a naive implementation of fuzzy c-means. So what we'd like to do is, I'm sorry, one additional thing that I want to explore is, we can use the TSNE plots to give us a sense as to, how insightful that particular fuzziness parameter was with respect to our data set that we're visualizing with the TSNE plot. It can also give us a sense as to, for instance, how well did, or to what extent did our fuzzy c-means clustering results agree or associate with what the TSNE plot was suggesting about the clustering structure. So normally, what we've done in the past is when we had a hard assignment or a partition-based clustering, we simply just took our TSNE plot and we color-coded it by the cluster labels. However, in this case, in order to extract insights about our fuzzy clustering membership matrix, what we want to do instead is we want to color code our same TSNE plot 10 times, or in other words, by each of the 10 column values in our fuzzy clustering membership matrix. So a little bit more information about the code that produces these plots. So this is a little bit more sophisticated subplot creation here. So for instance, what I'd like to do is create a I'd like to create 2 rows of plots and 5 columns of subplots. So I use this plot.subplot function. And really what I'd like to, or what I'm going to be using here is this axis object that I created. So basically when I'm creating each of these subplots, I'm going to be referencing this corresponding axis object that I've just created. Okay. And then what I'm going to do is I'm going to iterate through each of my 10 rows of the cluster, or excuse me, each of my 10 columns of my cluster membership matrix. Or in other words, this is going to actually correspond to each of the 10 rows in that W matrix, which has yet to be transposed, if you will. So basically, again, you want to remember the row in this W matrix corresponds to a given set of cluster membership scores for a given cluster. Okay, so essentially what I'm doing here is I am taking my DF combo data frame, which contains like my TSNE coordinates, and I'm creating like another column, which is going to be temporarily just comprised of the, for instance, cluster 0 membership score values. Okay. Now take note, basically I need to create this color bar to the right of each of these subplots that I'm creating here. So I'm actually going to run essentially the same code twice. So the first code that I'm going to run is for the purpose of creating this points object here, which I'm going to use later on here when I actually create my color bar. But basically this points object is going to be an object that is going to correspond to a particular scatter plot that I'm creating. So the scatter plot is going to have, my TSNE coordinates, for my X and Y axis. And then what I'm going to do is I'm going to color code each of my points by this cluster membership score for that particular column. I can specify a color map here. So this is corresponds to dark green and white. And then another important thing that I want to specify here is that I want to specify that the lower bound for each of these color bars should be 0, and the upper bound for each of these color bars should be 1. Because the thing is, if I don't specify the upper bound and the lower bound, what this color bar is going to do is it's actually simply just going to pick the highest value that it ends up seeing in this particular row, and the lowest value that it ends up seeing in this particular row. So it doesn't really give you a true accurate reflection of the percentage or the percent that a given observation corresponds to that given cluster. So this is something that we need to be careful about specifying for interpretation purposes. And then basically what I'm going to do here is I'm going to rerun that entire code again, essentially. So I'm going to be using that scatter function. But in order to modify or basically update the corresponding subplot, instead, what I need to do is I'm going to be applying that scatter function to the particular axis object that or the particular subplot that I am modifying at this particular iteration. So essentially what we're stipulating here with these 2 values inside of this axis object is basically the row and the column of the subplot that we are modifying here. So basically, if you know that you are iterating through 10 observations, so I equals 0 to I equals 9. If you want the first 5 observations to basically show up in the first row, or like the row with index 0, what you can do is you can simply just take that I divide by 5 and, calculate the floor of that value. So basically round down. And then so basically 5 to 9 divided by 5. If you round down, you get 1. Okay. And then if you want, and then basically just stipulate the column, what we're using here, this percentage, is the modulo operator. So basically this represents the remainder of what you would get if you had divided that I value by 5. So basically, 0 divided by 5, you get a remainder of 0. 1 divided by 5, you have a remainder of 1, so on and so forth. So basically what's going on here is we are specifying we're translating a given I value to a given set of row and column coordinates for the subplot that we're modifying, essentially. So yeah. Okay. So just a couple other things that I wanted to mention. Yeah. So basically, to add the color bar, how do I do this here? I think I've run out of colors. We're updating the coordinates here. And to create the color bar, we're basically saying, use the corresponding set of points, or basically use the scatter plot that was created here. And then this is you're specifying the particular subplot here that you're modifying, if you will. Okay, so this is this is what we end up getting when we color code our TSNE plot by each of the 10 cluster membership scores. Okay, so question for you guys. So what do we think? Do we observe a lot of association between what the TSNE plot was suggesting about the clustering structure and what fuzzy C-means was suggesting about the clustering structure? So you can say like high degree of association, somewhat of an association, no association. All right. Well, so for instance, I mean, you can see like this particular, cluster. Yeah. So most of the observations have one cluster in which there is, a cluster membership score of 1. And then the remaining clusters, they have a cluster membership score of 0. But, for instance, we can see that this TSNE plot suggested cluster here has a very strong association with cluster 4. On the other hand, it looks like fuzzy C-means cluster 2 ended up getting assigned to multiple TSNE plot suggested clusters. So what that might be an indication of is that, the cluster 2 might actually have some meaningful separations within it, for instance. And then, some other things that we might take note of. So for instance, like this cluster here, so cluster 7, does seem to have a strong association with just one and only one TSNE plot suggested cluster. So, we would feel more confident about fuzzy C-means cluster 7 because we don't really see, we do see like some evidence that there is, a strong separation between observations mostly assigned to this cluster versus, observations mostly assigned to like this cluster here. On the other hand, it seems like we might to some extent be setting ourselves up for failure. So you might have interpreted that there's actually, for instance, like 13 TSNE plot suggested clusters. So given that, we were only looking for 10 clusters in fuzzy C-means, it might make sense, for instance, that, fuzzy C-means cluster was comprised of, for instance, multiple TSNE plot suggested clusters. So what this might indicate to us is that, it might be a good idea to also explore a higher number of clusters in fuzzy C-means. But another key thing, like essentially what we're doing in this analysis here, which is not necessarily complete analysis, we're focusing more on, did we select the best fuzziness parameter, P? And so basically, again, we're seeing evidence that this is, what we have seen before. This is a very hard assignment. And it's kind of like, well, what's the point? What was the point of using fuzzy C-means if most of our observations, including the straddle nodes, which we're showing up here, have a very hard assignment, right? We might as well have just used k-means, which was computationally, or much more computationally efficient. So we can use this TS&E plot to give us suggestions about what an ideal fuzziness parameter might be, such that we actually are reflecting, the cluster uncertainty that we might expect for, these straddle nodes that exist here. Now, this is all dependent on you relying on the TS&E plot. So we want to remember, the TS&E plot, it's not necessarily the right answer every time. So there's some clusters that the TS&E plot is not going to detect. So this is, like, we're simply just using the TS&E plot as a way to corroborate our answers, but we want to make sure that we're never viewing it as like the answer key. Just to emphasize that again. So any questions on that? Okay, so let's actually use more intelligent parameter tuning to help us, at the very least, tune that P parameter. So we're basically going to run through the same set of code again, but we're going to try out multiple values of P. So we're going to use this linspace function to basically iterate, or basically create 6 P values, which are going to be 6 values that are equally spaced between 1.01 and 2. Okay. And really the only thing that's going to change is the value of P that we're going to end up using in the C-means function here. Okay. So based on these different values of P, let's see what kind of results that we end up getting. Okay, so this is the same value of P that we used before. Okay, and we can see that again, yeah, this is, if we color code our TS&E plot by each of the 10 cluster membership score values, we can again see that this is a, very hard assignment. Now, an additional cool thing that we can extract from this particular fuzzy C-means clustering is we can explore what each of our fuzzy C-means centroids looks like, because this is an image data set. And so, for instance, we can see, let's take a look at cluster 4 here. So we saw that, cluster 4, had a very strong association with one and only one TS&E plot suggested cluster. So this, this builds corroborating evidence that cluster 4 is meaningfully separated from other observations in the data set. We can also see that, those observations with high cluster 4 membership weights were almost exclusively those that were zeros. And so if we take a look at what centroid 4 looks like, then yeah, we can see that, yeah, the weighted average of each of the observations in the data set does in fact look like a 4. So that all that makes sense. On the other hand, if we take a look at cluster 2, yeah, let's take a look at cluster 2. So we can see that cluster 2 is actually comprised of a couple of types of digits. So it's like a combination of these values here. So it looks like a mix of 9s and 4s and a couple of 8s as well. And when we take a look at what that centroid looks like, it mostly looks like a 9. That that makes sense, but it's not a very it's kind of a confusing 9. And then also, for instance, if we take a look at cluster, let's see, which one do I want to focus on here? Centroid, or let's do cluster 0. So we can see that is mostly comprised of these images here, which looks like some 1s and some 9s. And we can see that this, by taking a look at what the centroid for cluster 1 looks like, you can see that this might be comprised of the people who write a 1 like this, for instance. So yeah, so these are all useful insights that we can, learn about the, what types of clusters that we're detecting here. But ultimately, if this was the fuzziness parameter that we wanted to go with, this was using fuzzy c-means was kind of useless. It didn't really reflect any cluster uncertainty. So if we wanted to give our fuzzy c-means clustering algorithm more of an opportunity to actually give us a fuzzier assignment for certain observations, we could increase that fuzziness parameter to be something a little bit higher. Okay, now what we're seeing here is that some observations in this data set still have very hard assignments. So for instance, or the most part, all of our 0 digits have very hard cluster assignments to 4 and only 4. On the other hand, though, we notice that, these 2 clusters here that we observed in the TSNE plot, so those that are mostly comprised of 3s and 9s, so these 2 clusters do have some straddle nodes that exist between them. And so, for instance, we can see that cluster 2 is mostly comprised of the 9 digits, and that there's some observations which are more well nestled, I guess you could say, within the cluster. There's some observations that still have relatively high cluster membership weights, but we can see that the observations that are particularly on the border between these 2 clusters do end up having lower cluster membership weights, thereby reflecting more of that uncertainty as to whether they should belong to cluster 2 or cluster 9, for instance. And so we can use this insight to maybe, examine some of these observations that did end up having this lower cluster membership score. We might ask ourselves, what do these images look like? Are they 3s and 9s that are like not as well drawn? So by examining those observations, that also might give you a sense as to like which images do we think our supervised learning algorithms are going to have an easier or more challenging time with. Okay, so we got a lot more fuzzy insights from this data set simply just by looking at the TSNE plots. Okay, any questions on that? Okay, well, so we might be asking ourselves, well, okay, one additional thing that we can see here is, for instance, if we, again, find the highest cluster membership score for each of the observations and put that into a histogram, we do see, this corroborates what we saw in the TSNE plots as well. So it shows us that most of our observations still have their highest cluster membership weight to be assigned to one and only one cluster. But there now are a much higher percentage of observations in which their cluster assignment is much weaker to one and only one cluster. So this is, again, showcasing to us much more uncertainty about what cluster they should be assigned to. And then we also see that reflected in the normalized Dunn's partitioning coefficient, which is 0.176, which is a lot lower than 1. So basically, the lower your normalized Dunn partitioning coefficient, the fuzzier that clustering membership matrix is. And so let's keep going. Let's see, what kind of insights might we get if we increase that fuzziness parameter to be even larger. Okay. And so here's what we get if we color code our TSNE plot with each of these resulting 10 cluster membership scores. So what do you guys think? Do you think this is a super useful insight? So if you had to pick, which fuzziness parameter do you think was more insightful? So the one with 1.4 or the one with 1.2? Mhm. Yeah, yeah, I agree. So we can see, from the TS&E plots, like the observations that we might think should have a higher cluster membership score, i.e. those that don't really straddle multiple clusters, they do in fact end up having more certainty in their cluster assignment. And that's what we would want. On the other hand, we are allowing for some observations to have fuzzier cluster membership scores, particularly those that are straddle nodes. But essentially what we see here is that, when we increased that P parameter to be 1.406, we're not really getting a whole lot of insights. So basically what we're seeing here is that most observations are basically cluster 0. Most observations belong to cluster 0 about 10%. Most observations belong to cluster 1 at a level of about 10%. So basically, what this is saying here is most observations, except for like a few here and except for a few here and here, what this is saying is most observations belong more or less equally to all clusters. So we can see with this TS&E plot, that's not a clustering relationship that's actually going on in this data set. However, there still are some slightly useful insights from this overly zealous P parameter that we can extract, for instance. So, what is interesting is that despite how high this fuzziness parameter was set, most of the 0 images still did actually have a high membership score to one and only one cluster, so cluster 8. And then the same thing for the 6 images. So they had a high cluster membership score to one and only one cluster. So what that might be an indication of is that, digits 0 and 6 might be considered the most distinct clusters from the rest of the observations in the data set. So what that might indicate to you is that, a supervised learning algorithm may have the easiest time detecting the 0s or perhaps the 6s from other images or other digits, if you will. Okay. And interestingly enough, so we also see this extreme fuzziness represented in the corresponding cluster centroids, where for instance, if you calculate the weighted mean of all observations, or basically if you calculate the centroid for cluster 5, we do see that the weighted mean of those observations corresponding to cluster 5 does in fact look like a 6, so that's what we might expect. And the centroid for cluster 8 does in fact look like a 0, so that's also what we might expect. On the other hand, though, for the most part, for the remaining centroids, they look like basically just like what you would get if you took an average of all observations in the data set. And that's essentially what we might expect here, because basically all of the weights for cluster 3 are more or less all the same. So essentially what that means is we're taking a equally weighted average of all observations in the data set. So again, these centroids are not super useful as well. And again, we can also see that, like, for instance, the highest cluster membership score for most observations in this data set is 10%, or 1/10, 1 over the number of clusters. Okay. So if we kept going by setting that fuzziness parameter to be even higher, so 1.604, at this point, we're not getting any useful insights at all. We are simply just saying that every observation belongs equally to every cluster in the data set. So at this point, we're not actually assigning any certain cluster assignment at all. So this is not very useful. And similarly, if we go, if we set that P value to be, even higher, we get the same result. And we end up getting a normalized Dunn's partitioning coefficient of something that is very low. Okay. So given, the sets of results that I've observed, if I wanted to basically give my client, if you will, the most insightful set of results, what I would end up going with, sorry, this is kind of zooming all over the place. The optimal parameters I would end up going with would be the ones that correspond to this fuzziness parameter value here. Okay. Now, in a more complete analysis, I might also try modifying the number of clusters as well. But if I knew that I was sticking with this number of clusters, at the very least, this is going to be the most insightful fuzziness parameter that I've tried, because again, it reflects the more certain cluster assignment of observations, which we might think should be more certain, and it reflects the less cluster, or it reflects less cluster certainty, cluster assignment certainty for those observations, which we might think are straddle nodes. Okay. All right, any questions on that? Okay, just a couple of more things that I wanted to explore with the final clustering that I have settled on. So the 1.208 fuzziness parameter. So basically I ran that algorithm one more time and I created my resulting cluster membership score. So give me 1 second. So this is what I settled on. And yeah, so if I wanted to, perhaps explore my final clustering a little bit more, there's some additional insights that I could extract from that. Let's see, a couple of other things that I could discuss. So for instance, if I wanted to examine, so let's just say, for instance, we observed that, the 0 digits tended to have some of the highest cluster membership scores for a certain subset, or basically they tended to have some of the hardest assignments, regardless of how high we set that fuzziness parameter to a degree. So we might be curious to explore a little bit more about those 0 digits. So for instance, are there some 0 digits that have perhaps lower cluster assignments or lower membership scores for cluster 4? And we might ask ourselves, well, what do those 0 digits look like, for exploratory analysis purposes? So for instance, what we can do is I can iterate through each of my digits in the data set. And I can take my highest cluster membership scores and this series that I've created. And again, this is the highest cluster membership score that corresponds to every observation in the data set. And I can filter, for instance, just for the 0 digits, or the 1 digits, or so on and so forth. Okay. And I can simply just choose to visualize the highest cluster membership score values for the 0 digits, and then the 1 digits. So basically I'm seeing, for instance, again, the 0 digits have, very high membership scores to one and only one cluster. And I see the same thing for digit 1, digit 2 for the most part. But yeah, then interestingly enough, like digit 8, which shows up in these observations here, digit 8 looks like it ends up having, the digit 8 highest cluster membership score values actually, do not tend to be close to 1. So what that indicates to us is that digit 8 ends up being assigned to multiple clusters in this data set. And we end up seeing that here in the TS&E plots as well. So these are my digit 8 observations here. And that shows me, for instance, like digit 8 sometimes is going to have a high 5 cluster membership score. It has, higher 9 cluster membership scores, but it never really has a hard assignment to one and only one cluster. So what that is indicating is that, what that might suggest is that the zero, or excuse me, the 8 digits tend to be the least distinct when it comes to the rest of the digits in this data set. So that might be an interesting insight as well. Okay, all right. So I see that it's 4:30, so I'll give you guys just a second, about a minute to check your emails, and let me check my email as well, just to make sure that those emails are going out. One second. Okay. Okay. All right, cool. So I do see that my emails have gone out. So again, if you've been selected, you can log off the lecture. If you haven't received any email, you can let me know, and I can tell you if you've been selected or not. But hopefully everybody should have received an email. Okay. Okay. All right, so I'm going to assume that everyone who is still here has not been selected. If you're unsure, again, let me know in the chat. But yeah, so we'll just wrap up with this MNIST dataset analysis. So what we saw was that, for instance, the 8 digits tend to have some of the lowest cluster membership scores to any one particular cluster. So we might be curious as to, why is that? Why is 8 more difficult? Or why did 8 not really strongly associate with a particular cluster or any one particular cluster in this analysis? So what we might decide to do is create a cluster membership matrix that is just comprised of the 8 digits here. And then what we can do is we can calculate the median cluster membership score of each of the digit 8 cluster membership score columns. Okay. And so what this shows us, or what this reflects to us, is more of that digit 8 cluster uncertainty. So it shows us, if we had to pick a cluster that digit 8, had the highest degree of membership for, we would pick, the one with the highest median value of 0.26, right? But for the most part, this is not a really high median cluster 5 membership score value. So again, this shows us a lot of, there's a lot of uncertainty as to what cluster any one particular digit 8 should belong to. But it does seem like, if we had to pick a cluster 5 tends to be the highest, or the cluster that it has the highest association with. And so I'll skip over some of these here in the interest of time. So for instance, what we might want to do, or what we could do, is we can visualize let's just say the cluster 9 membership scores for the digit 8 images. And we see that for the most part, most of our digit 8 images do not have a very high membership score for cluster 9. We do see some observations do have a relatively high cluster 9 membership score. So for instance, if we take our digit 8 membership scores and we sort those values, we can see that the image with index 1675 does in fact have the highest cluster 9 membership score. So we might decide to, visualize that image to see, well, why did this image end up getting lumped with cluster 9, which is mostly comprised of other types of digits? So this is what that 8 digit looks like here. So what we want to remember is that cluster 9 in our particular clustering actually ended up looking, it ended up being comprised of mostly 3 digits. And so by looking at this 8 image, this is not a very well drawn 8. It's kind of hard to tell that this is even an 8. What that is suggesting, or what fuzzy C means is suggesting, is that this 8 looks most similar to the 3 digits in this data set. So that might be why this 8-digit ended up getting placed in the cluster of observations that is mostly comprised of 3s. So this can give you some more interesting exploratory, preliminary exploratory analyses that you might find insightful if you want to build some sort of a predictive model that actually predicts the digit a particular image is of, essentially. And yeah, a couple of other things. But yeah, so let's contrast that with the 0 digits, because we do see, we were seeing much more certainty, or much more of an association with the 0 digits with one and only one cluster. So let's, by comparison, explore the 0 digits. So what we can do, again, is we can take our cluster membership score, our cluster membership matrix, and filter it for just the 0 digits. Now take note here, when we calculate the median membership score for the 0 digits, we do see much more of a strong association with one and only one cluster. So cluster 4 has a median membership score of 0.99, which indicates that, most, the median value that a particular observation, particular 0 digit belonging to cluster 4 is very high. But there is some, assignment to other clusters as well. So someone's asking, why do we use the median instead of the mean? So you could technically use the mean as well. We want to remember that the median tends to be more robust to skewed distributions and outliers. Now, technically, I didn't. And basically, what we're seeing, if you take a look at the histogram of like this set of observations here, this is going to be a very skewed distribution. So the median is going to be more reflective of the central point of that distribution. But you could have used a mean as well. But I think the median is going to be more insightful given the skewed nature. Yeah. So I'm seeing a private message here. So just give me 1 second. So a couple of other things I think I wanted to, just skip over that in the interest of time. Yeah, so this is mostly just kind of, further exploring like, why particular images had higher or lower cluster membership score values to one particular cluster, if you will. And so the final thing that you might want to do with a fuzzy clustering is try to utilize some of the other clustering evaluation metrics that we have discussed in the past. So for instance, you might be interested in taking this clustering and for instance, like calculating the average silhouette score, making like a silhouette plot, using a cluster sorted similarity matrix to learn a little bit more about the clustering that you've created. However, the downside is that all of these clustering evaluation metrics that we've discussed so far, they're only meant to be applied to partition-based clusterings, whereas we're dealing with a fuzzy clustering membership matrix. However, that's totally fine. So if we ever want to translate a fuzzy clustering membership matrix into a partition-based clustering, all we really need to do is basically, 1 second, all we need to do is basically take each observation and simply just assign it to the cluster that it has the highest cluster membership score value to it. So for instance, this observation would be assigned to cluster 4. So the code that does that would be Da-da. So what we can do is take that fuzzy clustering membership matrix, and I'm going to transpose it, okay? And I'm going to focus on the ith row of that transposed matrix. And I'm going to use the argmax function. So basically, let me just take this here. So basically what that's doing is it's, for each row in my fuzzy clustering membership matrix, it's finding the maximum value, or basically the maximum cluster membership score. So that would, like, if I simply just used max, it would simply return something like a 0.99, or basically the highest cluster membership score. But because I'm using the argmax, what the argmax function does is it finds the index of the value that gave you that highest value, essentially. So for instance, for a given observation, so basically for the row 0 in my cluster membership matrix, if the fourth cluster had the highest cluster membership score, then this argmax function would return that number 4, if you will. Okay, so basically I'm doing this for every I in the range of rows, or basically the number of observations in my data set or my cluster membership score. So basically this gives me a set of, or basically a list of cluster labels that correspond to every observation in the data set. Okay. Yeah. So someone's asking, like, so essentially what I'm doing here is what's called list comprehension in Python. So I briefly discussed it last week, but basically it's a way to iterate through a for loop and create, or basically update a list of values based on the particular, value in that for loop. So basically, if you wanted to do this a different way, you could create a for loop like this, and you could say, I'm going to append to this particular list this corresponding argmax value here. So basically what that does is it creates a list of cluster labels, which I add on to as a new column to my DF data frame here. So for instance, what this would indicate to me is, this belongs, this particular observation belongs to, so this would be, oh, sorry. Yeah. So basically what this final column would be, it would be an indication as to like what cluster or what cluster label each observation correspond to. So on and so forth. Okay, so you can basically take these hard or these partition-based cluster labels that you just created, and you can use them as input into like your average silhouette score calculation, your adjusted RAND score calculations, any of the partition-based clustering evaluation metrics that we discussed. Okay. I think we can skip over these things here. Okay, yeah, so that basically concludes a couple of insights, so some useful insights that we can extract from the fuzzy C-means clustering algorithm. And again, the main benefit of this algorithm is that it allows for us to reflect more nuanced cluster membership scores for observations that should not necessarily belong to one and only one cluster. So it gives us more useful insights about cluster uncertainty, which might be inherent in some data sets, particularly those that have not well separated clusters. Okay, any questions on that? All right, cool. I guess in the last 6 minutes, we'll move on to Unit 10, which is going to be about principal component analysis. Now, I am curious because I know that in other classes, a lot of us might have been exposed to PCA before. So I wanted to ask you this first. Who here has seen PCA before in one of your classes? Okay, cool. So I'm just going to end the poll. Okay, so it looks like for the most part, a lot of us have already seen a PCA before. Now, I think from what I've heard from students that I've taught in previous semesters, the main reason why they were using PCA was for the purpose of what we call principal component regression. Or in other words, and correct me if I'm wrong, or in other words, one of the benefits of using principal component analysis, which is a dimensionality reduction algorithm, is that you can basically represent your explanatory variables in a slightly different way. But the benefit is in the presence of multicollinearity. So sometimes we take our original set of explanatory variables, which might have strong linear relationships with each other, and if we choose to represent the set of explanatory variables with the principal components, then we've essentially gotten rid of the issue of multicollinearity. Now, one of the benefits, or one of the properties that we're going to end up seeing in this PCA dimensionality reduction is that the correlation between any pair of variables or any pair of projected variables is that correlation is going to be zero. So we can actually use PCA for a wide variety of different applications. So in that principal component regression analysis or discussion that I just talked about, that's mostly for the purpose of using principal component analysis for supervised learning purposes, or in other words, using it as a way to enhance your supervised learning analyses. But now technically, principal component analysis at its core is an unsupervised learning analysis. So in particular, it's a dimensionality reduction algorithm. So we're simply just asking ourselves, how can we represent an original high dimensional data set with a lower dimensional data set such that some aspect of the original data set is preserved? So for the there's a wide variety of uses that PCA can serve, but basically this is an unsupervised learning analysis class. So basically our main goal is to use these algorithms to learn as much as we can about the underlying relationships that exist in the data set. So the main thing that we're going to be focusing on here with PCA is how can we use PCA to learn more about what's going on in our high dimensional data set. So someone's asking, how are TS&E and PCA related to each other? So that's a good question. So what we want to remember is that PCA and TS&E, they are two types of dimensionality reduction algorithms. So what we want to remember is the dimensionality reduction algorithm, it's always trying to preserve something about the original data set. So we're actually, this is actually a question that we're going to get to in just a second here. So I might just kind of wait till we actually get that here. But the main distinction is what we are preserving in PCA versus TS&E. So we'll get to what that is in just a second. But I want to talk a little bit more broadly now about what dimensionality reduction algorithms are actually doing. So generally speaking, when it comes to describing a dimensionality reduction algorithm, we usually start with some original data set, which contains, M objects and N attributes. Now, in any dimensionality reduction algorithm, there's some sort of transformation function, T, which takes our n-dimensional data set and it represents it with some p dimensional data set. Now, usually this p is a lot smaller than the original number of dimensions n. And so the data set or the the projected data set that we end up using is always trying to preserve, like we said, some structure, some aspect of the original data set. So this function t can be more or less basic depending on the type of algorithm that you're using. So a more basic dimensionality reduction function t could simply just be a n by p matrix. So for instance, if you have some n-dimensional observation, you can simply just take this matrix t, multiply that observation by t, and get y, which is going to be a new observation with p attributes. On the other hand, rather than transforming just a single point or a single observation with the matrix t, you can take an entire matrix comprised of rows of observations, and then basically multiply each of these rows by your matrix t, and then get a lower dimensional representation of each of those rows from X. So I guess we'll talk about this on Thursday, but for instance, a basic dimensionality reduction matrix T can simply just be this matrix here. So for instance, we could choose to project the observations X1 and X2 onto a lower dimensional observation or two sets of observations using this matrix here. So something to think about as we're waiting for Thursday's class is, yeah, if we use this matrix T as our function, if you will, or basically as the matrix which is creating the projected data set, we want to think to ourselves, well, what aspect of the original data set is this linear transformation T preserving? All right, so we'll talk about that on Thursday. Okay. All right, so I will stop recording.